So previously we had the term-by-term differentiation theorem that said that if you had a power series, you could think of that as a function, and that function was differentiable over the whole interval of convergence. And the way you obtain the derivative, it was exactly how you would guess. You just go through that power series term by term, differentiating by the power rule. And the reverse is also true. So term by term integration theorem says if you have a power series there and you have some non-zero radius interval of convergence, then the function there, f of x, is not only integrable, but integrable over that whole domain, over that whole interval of convergence. And notice we've got the plus c in there, right? There's always a constant of integration. So what I want to do is run through an example with the same one we did with term by term, because that's a nice example since we know what function it's equal to. So let's start with this guy that we had, our most basic power series. To remind you, that thing, what was nice about that is it's geometric. Not all power series are, but that one's geometric, so we knew this thing, which is 1 plus x squared and so on, is actually equal to that. And remember, we knew that because this is geometric. A is 1, r is x. So a over 1 minus r. But that's only true when the radius, when that r from our geometric is less than 1 in absolute value. OK, so now let's integrate both sides, term by term integration. So on this side, when I integrate this, what term by term says is you just integrate it as if you were integrating each one of these terms, anti-differentiate, or in general there, the power would go up by 1, divide by the new power. Or thinking of it term by term, that's x plus x squared over 2 plus x cubed over 3, and so on. Plus a constant. I'll go ahead and put it on the other side. Since I have an equal sign, I could really put the constant on either side. But since I forgot to put it here, I'll just put it on the other side. Integral of that, power rule, that's to the -1. But by chain rule, I have to divide by -1. So all I've done is I know how to take the antiderivative of this function, but now I know how to take the antiderivative of that series because of term by term integration theorem. And this is interesting because now we finally have something where we're headed towards this idea of a Taylor series, right? Of a function written as a series. And although this is a function written as a series, this is a function we already know how to compute. We already know how to take 1 and divide it by 1 minus a number. Here, finally, we have something transcendental, natural log. We don't know how to compute values of that. And so now we're kind of getting somewhere. We've got a transcendental function written as a series. The only problem is this constant of integration. We're going to need to know what c is. So if we could find one value of natural log that we actually know, we could solve for c. And there is one value we know. We know natural log of 1 is 0. So that would mean an x of 0. So if we let x be 0, notice everything on the left, this is nice, is 0. Here, we have negative natural log absolute value of 1. But that's 0. That's the reason we picked 0 there. So we'd have natural log of 1, which we know is 0. So it turns out in this case, for this particular function, the constant of integration is 0. So what we have now, and I'm going to write this the other way around with the function on the left. So now we know that's 0. So this function equals that series. So negative natural log absolute value 1 minus x is equal to that, x plus x squared over 2 plus x cubed over 3, and so on. So, what could we do with this? Well, we could calculate values of natural log by plugging in values on this side instead. The only problem is there's infinitely many terms here, right? So what I want to do is let's look at an example, and what we'll do is we'll just bring in terms doing partial sums, right? We could sum up the first term, first 2 terms, first 3 terms, and so on. And I want to see how those get better and better. So let's just do an example. Let's look at, say, natural log of 2. Let's try and figure out what that equals. Well, this is a little bit awkward. I'm going to have to write natural log of 2 in this form. And I'm going to take advantage of rules of exponents. Natural log of 2, or the exponent rule of logs, natural log of 2 is negative natural log of a half. So I'm getting close. Oh, and by the way, as a little remiss here, we should keep writing our domain. This is not always true, right? It's only true when x is less than 1 in absolute value. And the value we plugged in was 0. So I guess I didn't need to write it here, but I definitely have to write it back here. So we can't just do any old value in natural log. This has to be convergent, right? This has to add up to something. And this only adds up to something when x is less than 1 in absolute value. OK, so back to this. I've rewritten it as a negative natural log. And I want to write the inside as 1 minus something. So a half is 1 minus a half. So now I've rewritten natural log of 2 in a format that matches the way we've got the function. Now I'll admit that's a little bit awkward right now. Don't worry too much about this. When we get to Taylor series, we'll derive this in a much better form, so it's just plain old natural log of x, something a little easier to work with. But I've rewritten natural log of 2 as this, so that means x is a half, right? What's being plugged into this function here is a half. I didn't write absolute value because positive numbers is going to be positive. OK, so what does that mean? It means that right here, negative natural log, we know that natural log of 2, which I argued is the same as negative natural log 1 minus a half, is equal to what you get when you plug in a half into this polynomial. Power series, technically, because it's infinitely long. So 1/2 plus 1/2 squared over 2 plus 1/2 cubed over 3, and so on. So what we could do is we could just take the first term, a half. That would be some approximation just using this. So we could say natural log of 2 is approximately a half. Or we could say, if we want to be a little bit better, we could say it's a half plus a half squared over 2. If we want a little bit better, we could say it's a half plus a half squared over 2 plus a half cubed over 3. And every time we bring in another term, we're getting more and more detail. We're getting a better and better approximation of natural log of 2. So what I'd like to do now is to switch over to Desmos, and we'll take a look and kind of see how these approximations are getting better and better. All right, so what I've done here is I've put a series into Desmos, and I've named it S so I can keep track of the value. Now, it's a partial sum. So what I have is, this is our series, right? It's x to the n plus 1 over n plus 1, but I've plugged in a half. And I'm summing from 0 up to k. And what I've done is put a slider in for k. So right now we're adding from 0 to 0, so just the very first term, 1/2. And then I've got Desmos giving us what it thinks natural log of 2 is. So this is kind of our goal, to see if we can approximate natural log of 2. And then down here, I just want to look at the difference. So far, all we've done is add up the first term, 1/2. And there it is, 1/2. There's what natural log of 2 should be, or at least as to Desmos's accuracy. And there is our error. We're off already at the first decimal place, right? So now let's move this up to 1. Now we're adding up those first two terms, because we're going from n equals 0 to n equal 1. So that's 1/2 plus 1/2 squared over 2. And now we're a little bit better, 0.625 versus 0.69 something. And now our error we see is getting a little smaller. And then what we can do is keep bringing in more terms. So that's adding up the first 3 terms, 4 terms, 5 terms. And if you keep an eye on the error down there, we see that error value is getting smaller and smaller and smaller. We've added up 19, 21 terms. So at this point, let's say 27 terms, right, from 0 to 26. We're down to an error of 10 to the negative 10th. So we're right in about the first 8 or 9 decimal places. Pretty soon here, we're going to be as good as Desmos, right? 10 to the negative 12, 10 to the negative 14, boom. Now, are we exact? No, we are not exact. We are just as good as Desmos's approximation. All right, Desmos is only kicking out so many decimal places with what it thinks natural log of 2 is. And we've matched all those. So we are as good as Desmos now by using 45 terms. And Desmos is probably doing something similar to this to get its computation. I'm not 100% sure how it does its calculations, but this would be one way for it to do it, would be to actually use a series. And all it's doing is doing a series far enough that it is accurate to the number of decimal places it's putting on the screen. Right? Desmos doesn't need to know what natural log of 2 is past that last digit because it doesn't put anything else on the screen. So it doesn't know any more than it shows. So even though we're seeing an error of 0, this is still an approximation, right? Natural log of 2 is some irrational number. The decimals go on forever. So if we could store more accuracy in this machine, we could keep going and bringing in more and more decimal places. And that's going to be the idea of Taylor series when we get to those, is that we'll do this with all of our transcendental functions so that we can take approximations, use more terms. The more terms we use, the better the approximation. And that's sort of our goal here with series in general.